Hi, welcome to Linear Algebra. Today we're going to start with a brief introduction to some of the terminology and concepts that you'll need going forward into this course. So let's just start talking about the phrase linear algebra itself. Linear algebra is just the study of linear functions. So the word linear means straight or flat. One straight function that you're probably already familiar with is the regression equation. Here I've drawn such an equation in 2 dimensions. And the word linear also means that the function involves only addition and scalar multiplication. We'll never see any x squareds or x times y. But I don't want you to get too hung up on thinking about linear algebra just in the context of linear regression. While we will talk about linear regression, there are a multitude of other data mining techniques that require the language of linear algebra. This includes support vector machines, many dimension reduction techniques like principal components analysis. Pretty much any data mining tool can actually be formulated in the language of linear algebra. So just thinking about regression, though, in the real world, our regression equation and our modeling problems are going to involve more than 2 variables. So with 3 variables, we can still draw what that looks like, right? Our linear regression equation is going to be a plane, which is, again, a flat surface. But when we have more than 3 variables, we can no longer imagine that surface. However, because it's linear, we know that it's flat. It does not bend or curve. So we'll not see equations or functions like x squared plus y squared plus 3z equals 10 or these other equations involving square roots and logs. All of these functions are nonlinear. Again, a linear function only involves scalar multiplication and addition or subtraction. Some examples are listed here. Certainly we can have as many variables as we need. So linear algebra is going to require the study of matrices and vectors. So these objects are at the core of almost every data problem that exists, right? Our data is really just a big matrix, a big table of numbers. A matrix is just an array of numbers, logically ordered by rows and columns. So for example, I have 2 matrices here. And a vector is simply a matrix with only 1 row or column. Some examples are here. And then a scalar is just a number. For example, pi, or 2, or 10 to the 16th would be a very large scalar. So to numerically work with data, any system is going to turn that data into a matrix. So here I have some simple numeric data with a credit score and some income, and the names of individuals. Now, the names here are row identifiers, which don't really go into the data algorithm. We're not going to put someone's name into a regression, for example. But we would use their credit score and income. So those variables would become columns of our data matrix. And so before we can really begin to talk about the arithmetic of using matrices and vectors, it's very important that we know how to describe them. So we're going to talk about 5 things in the course of this chapter: the size and dimension of a matrix, IJ notation, just some general notation, the transpose and symmetry, and also some special matrices. So we'll start with the size or dimension of a matrix. The dimensions of a matrix are merely the number of rows and columns in the matrix. So that's pretty easy. The number of rows is always specified first. So an m by n matrix, m rows, n columns. This m, the rows, will always go first. So here we have 3 rows, 2 columns. So A is 3 by 2. H is 4 by 3. And sometimes we'll go ahead and specify the dimensions of the matrix as a subscript so that we know exactly what size that matrix is. Now, if these were data matrices, then this would tell us how many observations and how many variables we have in our data set. square matrix is just a matrix that has the same number of rows and columns. So it's n by n. So A here is a square matrix, 3 by 3. H is not a square matrix. It's called rectangular because it's 4 by 3. Now, a vector is just a matrix with one row or column. So we'll often specify directly whether it's a row or a column. So a row vector is a 1 by n matrix because it has one row. And a column vector is an n by 1 matrix because it has one column. So as we work through all of these lectures, you'll hit these slides that say check your understanding. This is a good time to pause the recording, do the exercises that are shown on the slide, and then the next slide, when we come back, we'll have answers. Here's the solution to this slide. So B is 4 by 3, C is 7 by 4, T is 7 by 1. And any square matrix here will do. So now let's move on and talk about IJ notation. So the element in the ith row and jth column of a matrix is written Aij. Sometimes we'll use a small a, ij. And so the diagonal elements of a square matrix are those that have identical row and column indices, A, I. So if we want to refer to the ith row of A, we'll use the notation A, I star, where that star says every column. So we want the ith row in every column. And then similarly, A star j means take every row in the jth column. So that will give us the entire jth column of the matrix. So we can try this here. This red element here is in the third row, first column. So that's B, 3, 1 is equal to 3. C, 2, 3, that's the second row, third column, that's equal to 4. B, 1, 1, the diagonal element, fall along the main, we call this the main diagonal of a matrix because it is the longest diagonal that can be drawn in the matrix. And so diagonal elements are only defined for a square matrix. If we think about that for a rectangular matrix, here there is no main diagonal because that would go from corner to corner. Similarly, the first column of the matrix B would be star 1, right? All rows, first column. That would carve out this first column. The third row of the matrix C would be C3 star. Third row, all columns. This row here. So when it comes to vectors, we no longer need two subscripts because vectors only have one row or one column. So here we can just use a single subscript to reference the element that we want. Vi is going to be the ith element in a vector V. So here V3 is equal to 7, V5 is equal to 3, and P2 is equal to 0.3, the second element in P. So here's a good place to check your understanding. Pause the recording now. We'll come back with solutions. Here are the solutions to the Check Your Understanding slide. And now we'll move on to talk about IJ notation. So the nice thing about IJ notation is that it can help us define an entire matrix. Consider this data here where we have 6 different students and they're assigned to teams over the course of a school year. So there's 2 teams in each of the terms, summer, fall, and spring. So now we can define a matrix M to represent this data just by defining every element with one line. So Mij will be the number of times that student I has worked with student J, as long as I is not equal to J, and it will be set to 0 if I is equal to J. So let's think a little more about this definition. The I and J refer to students. So there are 6 students, so there must be 6 rows and 6 columns to this matrix. M23 would be the number of times that student 2 has worked with student 3. So looking over this table, we can see that happened in summer team 1 and fall team 1. So that's equal to 2. M33 is going to be equal to 0 because I is equal to J in that case. So the second part of this definition is going to refer to the diagonal elements. And that number 0 is chosen arbitrarily. Choosing the number 3 makes just as much sense. You could say that when I is equal to J, that means you're talking about the same student. So student 6 worked with student 6. Well, you could certainly say they worked together 3 times. Student 6 can't not work with student 6. Or you could just define it to be 0, which is what has been done here. And so that entire matrix is shown here. And if we look just at that first row, so the first entry is 0 because all of the diagonal elements are 0. The second entry is 2 because student 1 worked with student 2 twice, here as well. And student 1 worked with every other student 1 time. So they work with student 3, student 4, student 5, and student 6. And if we'd like, we can think of this data as a social network of students. And in a network, this matrix M is called the adjacency matrix because it tells us about how the students are connected or adjacent to one another. And we can draw what's called a graph of this network using 6 vertices to represent the students and some edges to represent their memberships on the same team. So a graph in this context is what you may already refer to as a network. It is a group of, these are called vertices or nodes, and they're connected by lines or edges. And we can let the thickness of the edge represent how often the students have worked together. So thicker edges here represent partnerships that have happened more often. So students 5 and 6 have worked together the most. They've worked together 3 times. Student 2 has worked together with students 1, 3, and 4 many times and has never worked with students 6 or 7. So this is meant just as a very small example to get you thinking about the different ways that matrices might be used in data analysis. It doesn't have to be your typical table of data. Oftentimes we're looking at networks or similarity matrices or other things that can tell us about underlying patterns in the data. Now we're going to move on and talk about general notation of matrices and vectors. In this course and in most resources that you'll find online or elsewhere, matrices will be named with bold capital letters. For example, M, P, A shown here, or even capital sigma will all be matrices. Vectors will also be bold, but lowercase letters. So V, U, P, even X sub 2, as long as it's bold, will represent a vector. And scalars will always be unbolded and lowercase, and sometimes Greek. So, for example, alpha, lambda, c. Here we have the element in the third row, second column of the matrix A, or the second element in the vector B. That would be a scalar. So you can see the difference here between V sub 2 and X sub 2. If X sub 2 is bold, then I'm probably listing a bunch of vectors, like X1, X2, X3 would all be vectors. And this notational convention will help us understand what we're looking at. So if an equation is listed as ax equals lambda x, which it will be in the future, we can immediately know what each part of this equation represents. A is a matrix, because it's capital and bold. X is a vector appearing on both sides. It's lowercase and bold. And lambda is a scalar. For now, we haven't talked about how to add or multiply these objects yet, but that's coming. So now you can check your understanding just by indicating what each of these notations represent, a matrix, scalar, or a vector. And the solution to that is here. And the last thing we're going to talk a little bit about today is vector geometry. You'll recall that ordered pairs are just coordinates, x1, x2, that live on the two-dimensional plane. In linear algebra, we call this plane 2-space. But our data in analytics typically has more than 2 variables. Say it has n variables. Well, then those data points are represented by n tuples, which are nothing more than ordered lists of numbers. So for every individual in my data set, I know n things about it, and I list that as an n tuple. Now, if I only had 2 variables, say height and weight, I could easily plot these on a coordinate plane using one axis for height and one axis for weight. I can't do that when I have n variables. So an n tuple simply defines a vector with those n elements. The idea of a point and vectors are interchangeable concepts. So what I'm claiming here is that this point that we used to think about on a plane is really a vector with 2 elements. The only difference is that a vector can be characterized by a direction and a magnitude. And we'll talk a little bit more about that in a minute, but you may recall that this R symbol denotes the scalar real numbers. Well, these numbers have a direction on the number line. Either they're positive, meaning they lay to the right of 0, or they're negative, meaning they lay to the left of 0. They also have a magnitude. The absolute value of each number tells us the distance between that number and the origin. Well, in linear algebra, we use the notation Rn to denote the set of all vectors with n elements. So if we write V, and this little symbol here means is in the set R5, we are saying that V is a vector with 5 elements. Sometimes you'll see something like A is in real 6 by 8, which means that A is a 6 by 8 matrix with real elements. So the idea of points and vectors are essentially interchangeable. In certain applications, it will help us to think about our data points in either one context or the other. So the way that they're interchangeable is that a vector is really a list of numbers, right? And so if I only had 2 numbers in that list, I could draw a point at each place where those vectors are giving me coordinates to. But a vector is really thinking about this arrow that points to that point. And so it has this direction away from the origin and towards that point, and also a magnitude, which is the length of this distance here. So it's a subtle difference between the two, the points and the vectors, but really our data points, or the rows of our data matrix, are both things. They're a list of numbers which define either a point or a vector, depending on which way you are thinking about it. Okay, that is where we're going to stop for today, and we'll come back tomorrow or the next time and talk about transpose and symmetry.